What is the math behind vector graphics scaling? Imagine resizing a drawing without losing any sharpness or detail. That's what vector graphics do so well, and it all comes down to some simple but powerful math. When you scale a vector image, you're changing its size without stretching or squishing the actual shapes in a way that distorts them. How does that work? Well, it's all about points and how they move. Every shape in a vector graphic is made up of points with coordinates, which are just numbers telling you where each point sits on a flat surface. These coordinates are written as pairs of numbers called x and y. When you want to make the image bigger or smaller, you multiply these numbers by a scale factor. If you want to double the size, you multiply each coordinate by 2. If you want to shrink it to half, you multiply by 0.5. This process is guided by something called a transformation matrix. Think of it as a special grid that, when multiplied with the points, moves or resizes them. For scaling, the matrix looks like this: a 2x2 grid with the scale factors on the diagonal. For example, if you want to stretch the image horizontally by 3 times and vertically by 2 times, the matrix would have 3 on the top left and 2 on the bottom right, with zeros elsewhere. When you multiply this matrix by each point's coordinate pair, it shifts the point to a new position. This math applies to all parts of the shape, including curves and lines. For curves like Bezier curves, the control points are also scaled the same way, so the shape stays smooth and proportional. Because vector graphics store shapes as formulas, scaling doesn't make the image blurry or pixelated. Instead, the software recalculates where every point should be and redraws the shape at the new size. If you stretch an image unevenly, by making the horizontal scale different from the vertical, the shape will stretch or squish in that direction. This is still handled by the same math, just with different scale factors. More complex transformations, like rotating or skewing, are also done with matrices. These matrices are multiplied together, combining different effects into one. This flexibility lets artists resize, rotate, and manipulate their art precisely without losing quality. It's why vector graphics are perfect for logos, icons, and illustrations that need to look sharp at any size. So, in simple terms, the math behind vector graphics scaling is multiplying each shape's points by scale factors using transformation matrices. This keeps images crisp and clear, no matter how big or small they get. It's a smart, efficient way to resize digital art without any loss of detail or quality.